what I'm going to do is I'm going to say a few extra words, but that will be optional. So I'm going to use a different pencil. On the other hand, many of you have had linear analysis. Many of you know what an eigenfunction is. Many of you know what an eigenvalue is. And you probably know that we're just sort of leading you around the nose around that idea that we're really dealing with eigenfunctions and eigenvalues. And so if you had that feeling, it would, I think it would do justice if I complete the picture and explain everything that we've been discussing in the last few days using that language. But if you're struggling with the course, you should not be listening to that. That will, it's unnecessary for you. In textbook, that's section 5.11. So here it is. So we've discussed operators. Operators operate on wave functions. In general, if I take a function and I operate on it, in general, you're gonna get some different function in general. So this is in general. But there exists special, very special functions and they're related to a particular operator, such that when you operate on that function, you get that function back, maybe multiplied by some kind of a constant. It could be a complex number, but it's some kind of a constant, i.e., it's not a function of space or time, okay? It could be complex. Let's try to see, yeah, so you know, those of you who are watching this, hopefully know that this is called, such psi is called an eigenfunction of an operator O. And what is lambda? That's right, is called an eigenvalue of an operator O. So each operator has a set of eigenfunctions and eigenvalues. Eigen comes from German, meaning one's own. So each operator has its own set of eigenfunctions and eigenvalues that do this thing. So there are usually many of them, and oftentimes we put a subscript n. Okay? And again, that spectrum of eigenfunctions and eigenvalues can either be continuous, in which case there's clearly an infinite number of them, or it can be discrete. And if it's discrete, it can be infinite discrete set or finite discrete set. Let's check let's check variance or standard deviation of the quantity O represented by this operator in a state, in an eigenstate. So this is called, these wave functions are called eigenstates. Okay, so psi, such psi I might go over time, but again, this is an optional part of the lecture, so I think it's okay if I go over time, because if you're watching it, that means you're just curious. So this is all in good fun. Let's check that standard deviation of the observable O represented by operator O hat in an eigenstate psi is 0. Okay, so this is, okay, so let's do this. So I have this, O, this, dx, and I'm not putting limits. Well, when O operates on psi, it spits the psi back. So we get, and hopefully this is normalized, so we get lambda. Let's do this. And I think you already see where it's going. O squared means you operate on psi and then you operate on psi again. Each one will spit out a lambda. It's actually very easy. Okay, we got average of O, we got average of O squared, and then sigma of O equals wow. An eigenstate of an operator O hat is a state of a definite value of that observable. It's a big deal. I can even put a box around it. When you make a measurement, you're going to get a definite value. And you're going to force the wave function to be into a wave function that corresponds to a wave function of a definite value of that observable. In other words, when you perform a measurement, the wave function turns into one of the eigenstates of the operator that corresponds to that observable. It turns or collapses into one of the you can think of this as a postulate of quantum mechanics. So you have observables, energy, momentum, mass, charge, whatever. They're represented by operators performing a measurement of that observable will collapse the wave function into one of the eigenstates. And what would be the corresponding value of the observable? It would be the eigenvalue. Let me see, eigenstate, one of the eigenstate, one. Okay. So the corresponding measured value of the observable will be an eigenvalue of lambda n that corresponds to the eigenstate psi n. So each eigenvalue comes coupled to an eigenfunction. Now, an observable can have a spectrum of eigenvalues and a spectrum of eigenfunctions. So how do you know which eigenvalue and eigenfunction you're going to get when you make a measurement? That's random, but it's distributed in accordance to probability. And now I will just say in words, because this is going a little bit beyond that. You can always express your initial wave function before the measurement as a sum of the eigenfunctions of the operator, right? You can always do that. The probability, again, this is either a sum or an integral depending on the spectrum. To get nth lambda and nth upon a measurement is given by square magnitude of Cn. Everything that we discussed in the previous few days fits this picture. So this is like a nice mathematical summary. So your initial wave function could be something complicated, but you can always express that wave function as a sum of eigenfunctions of an operator that corresponds to the observable that you're about to measure. You perform the measurement. The wave function will collapse into one of these guys, and hopefully they're normalized. So after the measurement, the wave function will be just psi n without the coefficient because it's pre-normalized. But before the measurement, the wave function was expressed in terms of the sum of psi n's. And the probability to get nth eigenvalue and nth eigenfunction upon a measurement is given by the square of the coefficient. And that's all the spilled beans. Okay, so that's really the core of quantum mechanics, quantum measurement. And I guess I could also add that in between the measurements, the wave function evolves according to the Schrödinger's equation. In between measurements, or in between measurement and the preparation, a preparation is also a form of measurement. So in between measurements, the wave function evolves according to Schrödinger's equation. Okay, and this is the whole thing, including time, space, and everything, the full wave function. What else can I add? So you see the Hamiltonian operator, out of all operators, it's a special operator because the Hamiltonian operator determines the evolution of the wave function in time. And it also serves as an operator that corresponds to the energy observable. When we perform a measurement of some quantity, for example, position, after that, the wave function evolves in accordance to Schrödinger's equation, and it will no longer be that impulse or spike or the Dirac delta function. It starts to spread out in some complicated way. But if you make the measurement of energy, you collapse the wave function to psi n times e to the minus I en over h bar times t. And the only evolution after that will be just that phase factor growing in time. You can think of this as, once you've performed the energy measurement, you know the energy, and the energy has to stay constant. So you cannot have other modes that correspond to a different energy just to conserve energy. You can also explain this fact that energy measurement is a special measurement, in that Hamiltonian operator dictates how the wave function evolves. And so if you've collapsed the wave function to a particular mode of the time-independent Schrödinger's equation, it will stay in that mode because that's how the Hamiltonian operator evolves that function. It will only its phase factor will grow, but it will stay in that mode. A lot more can be said about it, but it requires sort of in-depth use of linear algebra. And I decided to tell you this story in case you were curious how the whole machine works. But of course, if you're curious, you really should take a separate course on quantum mechanics, where all this will be explained in greater detail, including all the nuances, what happens if you have degenerate energies, and or what happens if you have a continuous spectrum versus discrete spectrum. There's a lot in here. But I thought that since we're at it, we came really close, I may as well talk to you about this thing. So this blue text is just all in good fun, just for you. Okay? Thank you.